And if you make the same resolution as we'll be putting out on a Planck map of the Earth, you see the difference between how, here they look a little different, here they're incredibly different. So what features do you notice when you look carefully at a map of the Earth? Well, one of the things you notice is there are some long, sharp features. So if you look down the middle of the Atlantic, you see this ridge down the middle of the Atlantic? It's very sharp, but it's very long. It covers a good part of the sphere. So it's a long, sharp feature. And you see many others. There are other, the edges of the continents. There are places here, places here. There are places on the Earth where you see these long linear features. How do you get long linear features on the Earth? The answer is you have to have some nonlinear effects. If you just excite the various natural modes of the Earth, and they're unrelated to each other, you just get noise. In order to have sharp edges, you must line several things up together, and you must have the same phase, so they'll all reinforce at that edge. When I look at this map of space-time at the beginning of the universe, it has no long, sharp features. Right? Where you think, well, I might see a little one over here, but when you rotate the map over and project it, so it's not at such a funny angle, what you see is there isn't really a sharp feature there. And in fact, when you're just careful observing of it or chart, you find that there's no variation in this map, which has variations that are part in 100,000, no variations to and those and correlations to a part in 10,000. So it means the forces that make space and time, that is part of cosmology, is you have to create space and you have to create time. You have to understand where they came from. The forces that created the space and time, the expansion of the universe, the long history of the universe, those forces are so linear that none of those cancel. We get random quantum fluctuations, but nothing couples them together to make sharp features. So that is very surprising because we know that, in fact, that gravity itself is very nonlinear. Think about the sharp features we saw after a long time period with these sharp edges in this spider web. But in the early universe, the variation is only a part of 100,000. The nonlinearity to giving us an extra feature, another part of 100,000 below that, we're within a factor of 10 of that. So with Planck, we're hoping to go down to a factor of 5. Already, we're able to rule out various models of how that period of inflation, where you take the quantum size thing goes up. It has to be a very simple model of inflation in order for you to be able to see what's going on. So this is what you can learn by just taking the data and studying it very carefully. Even just looking at it with your eye, you can start seeing some of these effects. So you can do cosmology yourself. If you have pretty enough data, you can do cosmology. If this was, 1753 and you had this map of the Earth, you would be the best geologist because you could see these features and it would be clear. Right? So now we're beginning to do the same thing for the universe as a whole. So now I'm going to show you the sum of several different things and then the movie that we made combining all this together. First, we're going to start near the Earth and fly through the universe, like Jodie Foster did in her movie, in Contact. So here we are starting out with the sun. And we're going to kind of deduct the planets because we saw them already in very detail. But now humans have mapped the location of about 1 billion stars. I hope it's working. Okay, as we go out, it doesn't take very long to get through 1 billion stars. And then we have to go back to what they did in the movie and make a French Impressionist painting of our own galaxy. Because our own galaxy has 400 billion stars, so we haven't even mapped 1 in 400. Now we see the local galaxies, our galaxy, Andromeda, Fornax, the local group. Ignore that feature, it'll come back in a minute. We're rotating around so we can see what our local group of galaxies looks like. It turns out we have to go a long way from our local group before we start seeing other galaxies. There's the first little one coming into view. Now several. more. Of course, we have to go out along one of those places where we've actually mapped. This kind of looks like Jodie Foster's movie with real galaxies. Now you see they turn red because only large red luminous galaxies and quasars can be seen at great distances with small telescopes. And now you see the fan-shaped patterns. And I'll show you the next movie that starts with the galaxies and goes out further. So there's the galaxies. You see the great wall just to the left of the center. And the large red luminous galaxies and the quasars. And then around that, the sphere, which is the light from the beginning of the universe. And we get to go outside that sphere to look back at it, just so we can see what it looks like. So you can see what we have mapped and published, and we're in the process of mapping another factor, but we've only sampled, in the billions of galaxies out of 100 billion galaxies, but it's a good start. So we have this fantastic picture of some quantum processes happening to begin what we think of as our universe. This accelerating expansion, and then this slowing, we call inflation, and this slowing expansion, which is when we build the galaxies and so forth, continue merging, and then the universe starts accelerating again. So back to the original picture that I showed you, where we're seeing what it looks like, over the history of the universe, where we think we've mapped out most of the 13.7 billion years, but only in samples. We're now trying to go back and make the map in much more detail. So let me show you the movie, because I'll be running over other things, and then you guys feel free to ask questions. So here is the movie we made about a year and a half ago. This is best watched from the dark screen. So I don't know if it will show there. We're going to start on the Earth in the Himalayas, the highest point on the Earth. Now this is real data. This is made from Google Earth, actually. Where the highest and the lowest point on the Earth is 28 kilometers. The radius of the Earth is 6,000 kilometers, so that's a part in 200 roughness. But the Earth on average is smooth to about a part in 1,000. The universe is smooth with a factor of 100 more than that. So now you can recognize your favorite places. So this is a real picture of the Earth. Here's the location of the man-made satellites. You see some of the Russian orbits. See further on some additional Russian orbits. The white orbit around there is a geosynchronous belt. It's almost continuously populated by communication satellites. They're roughly a degree apart all the way around. You see the geosynchronous? Now you see the moon. For a whole light second from the Earth. Now I have this part. You see the constellations around us that we look at. Get further from the Earth, they'll distort. You can see the dust, the gas, the flame of our galaxy. And again, we still have to paint the picture of the galaxy. Our local group.